This is a short tutorial discussing the concept of limiting reagents. In most of chemical reactions in the laboratory, one reactant is far more expensive than the others. To maximize the amount of product that we get from this reaction, which of course in industry means money, whatever the cheap reactants are added in excess. And by excess, we mean we add more moles than predicted by the balanced chemical equation. The expensive reactant is referred to as the limiting reagent. By limiting reagent, we mean once it's gone, the reaction stops, even though there are still other reactants present. Well, let's look at a chemical reaction we've looked at previously, which is the oxidation of metallic magnesium in the presence of gaseous oxygen to give us magnesium oxide, plus a lot of heat. If you've ever seen this reaction, the magnesium actually bursts into flames. Well, we've already balanced this chemical reaction. We have two magnesiums on the left side, two on the right side, two oxygens on the left side, two oxygens on the right side. So the reaction is balanced. But when we walk into the laboratory, if we have access to 20 grams of magnesium and only 10 grams of oxygen, what's the maximum amount of magnesium oxide we can produce? Is there a limiting reagent? If there is, which of these two reactants is our limiting reagent? Well, let's go through the math on that and see what we can find out. A typical limiting reagent calculation looks something like this. We've got our balanced chemical reaction. We know that balanced chemical reactions tell us about moles, not about grams. We're going to go ahead and draw our roadmap. We're going to start out with the grams of magnesium that we've been given in the problem. We're going to calculate the stoichiometric amount of grams of oxygen that we need to balance that chemical reaction. And then we'll go ahead and calculate the number of grams of magnesium oxide we can use. As always, we're going to start on the right-hand side of the page with an equal sign and the units of the material that we need, which are grams of oxygen. Then we're going to start on the left-hand side with what we know. We know that we've got 20 grams of magnesium. Well, our roadmap tells us that we need to convert grams of magnesium into moles of magnesium. So we're going to multiply by 1 over the gram molecular weight of magnesium, making sure that we physically cancel out the units so that if we accidentally flip this conversion factor, we're going to catch it. Well, now we know how many moles of magnesium we have when we have 20 grams. The mole ratio between magnesium and oxygen is 2 moles of magnesium for every 1 mole of O2. We're going to cancel out moles of magnesium. We now know the number of moles of oxygen that we need to have to totally react 20 grams of magnesium. Well, we were asked to find out information about grams of oxygen, so we're going to multiply by the gram molecular weight of O2. We're going to cancel out moles of oxygen, and now we know how many grams of oxygen we need to completely react 20 grams of magnesium. Well, if we chug that through our calculator, we're going to find out that we need 13.2 grams of oxygen stoichiometrically to completely react 20 grams of magnesium. Well, at the start of the problem, we were told that we only have 10 grams of oxygen available. We do not have enough oxygen to totally react the magnesium. That means O2 is going to be our limiting reagent. All subsequent calculations then are based on the amount of limiting reagent, which is oxygen. So if I would like to calculate how many grams of magnesium oxide I can form based on the amount of material I've been given, oxygen is our limiting reagent, and we will start out using the number of grams of oxygen we've been given. We're going to multiply by 1 over the gram molecular weight of O2, cancel out grams of oxygen to find out how many moles of O2 we've added to the reaction when we've added 10 grams. Well, our map tells us that we'll need to convert that to moles of magnesium oxide. It's a 2-to-1 ratio based on the stoichiometric coefficients in the balanced chemical reaction. That means for every 1 mole of O2, I'll produce 2 moles of magnesium oxide. I want to make sure that I physically cancel out the units so that if I accidentally flip that conversion, I have moles of O2 on the top, moles of magnesium oxide on the bottom. I'll see that those units don't cancel and I'll catch that. Now I know how many moles of magnesium oxide I can produce using 10 grams of oxygen. I'm going to multiply by the gram molecular weight of magnesium oxide, which is 40.299 grams per mole. Moles of magnesium oxide cancels out. And now if I go ahead and chug that through using my calculator, I find out that the maximum amount of magnesium oxide I can produce if I start with 10 grams of oxygen is 25.19 grams. If it turned out that the magnesium was our limiting reagent, I could have produced 33.16 grams of magnesium oxide. So you can clearly see by comparing those two numbers, I get a far lower amount of magnesium oxide based on the limiting reagent, which is oxygen.